So, multiplicative identity in real numbers is a number that when you multiply anything else with it gives you back that number. So, what is for additive identity? It was 0. What's the multiplicative identity in real numbers? Ariana? 1. So, the multiplicative identity is 1 since A times 1 equals A. So, now we're going to talk about the multiplicative identity matrix for square matrices. So for any square matrix, the identity for the multiplicative identity for that is going to be ones on the main diagonal and zeros and 0 for all other elements. Okay, so examples. So I, for a 2 by 2 matrix, would be ones on the main diagonal. The main diagonal starts in your upper left corner and goes down. So I'm going to put a 1 here and a 1 here. That's our main diagonal. And then it's zeros for every other element. So I, for a 3 by 3, will be ones on the main diagonal. 1, 1, 1. And then what do we put everywhere else? 0. We get the gist? Okay. So now let's just show if A is equal to -1, 2, 3 in my first row, -2, 4, -1 in my second row, and 5, -3, 2 in my third row, I want us to show A times I equals A. What are we saying I represents here? Not 1, nope. The identity matrix, right? I will represent the identity matrix. So now my identity matrix has to be for a 3 by 3, right? Since A is a 3 by 3. So we're going to have A, which is -1, 2, 3, -2, 4, -1, 5, -3, 2, times my identity matrix, which will also be a 3 by 3. And that's going to be 1 on the diagonals and 0 on the main diagonal, and then 0 everywhere else. And now we multiply. So how do we multiply? We multiply. Do we agree our product matrix will also be a 3 by 3? So we're going to multiply my first row times my first column. So -1 times 1 is a -1, plus 2 times 0, isn't that 0? Plus 3 times 0, isn't that 0? So do we agree our first element is just -1? Now we're going to do our first row times our second column. Well, -1 times 0 is 0. No point writing that down. 2 times 1 is 2. And 3 times 0 is 0. No point in writing that down. Now we're going to do our first row times our third column. -1 times 0 is 0. No point in writing that down. 2 times 0 is 0. No point in writing that down. 3 times 1 is 3. I'm going to now do this whole process 2 more times. -2 times 1 is -2. 4 times 0 is 0. -1 times 0 is 0. Then we're going to do the second row with the second column. -2 times 0 is 0. 4 times 1 is 4. -1 times 0 is 0. Now we're going to do the second row with the third column. -2 times 0 is 0. No point in writing that down. 4 times 0 is 0. No point in writing that down. -1 times 1 is -1. And last but not least, we're going to do our third row with all the columns again. 5 times 1 is 5. Everything else is zeros. Third row, second column. -5 times 0 is 0. -3 times 1 is -3. 2 times 0 is 0. And now the third row and the third column. 5 times 0 is 0. -3 times 0 is 0. 2 times 1 is 2. So did we show that A times the identity matrix gave us back A? Yes, we did show that. Okay, so some things we need to know about matrix multiplication. Is associative, but not capital N, capital O, capital T, but not commutative. Okay, so what does this mean? It means if I have A times B times C, and I leave them in this order and I multiply A times B, and then take that product and multiply it by C, it's going to be the same as A times B times C. If I multiply B times C, and then take that product and have A multiplied by that product. This is okay. But what's not okay is switching their placement. So commutative is saying A times B equals B times C. That is not true. And an example would be if A is a 3 by 2 matrix, B is a 2 by 5 matrix, we would have A times B, and that would be a 3 by 2 and a 2 by 5. And so would it match up the rows and columns that we need to match up? Yeah, but now if we were to switch it and I had B times A, that means I would have a 2 by 5 and a 3 by 2. Do these match up? No. So that's what it means when it says that it is not commutative. We cannot switch the order. And that's why I was stressing when we multiply, we have to write it down in the order it's telling us to multiply it. So if it says A times B, I can't write B first. A has to be written first. Are we good with that? Yeah? Okay. So now let's talk about, we talked about the multiplicative identity. Now let's talk about the multiplicative inverse. So we know for the, you don't have to write this down, but we know for the additive inverse, if we have A plus negative A, that gave us 0, which is the identity matrix, which is the identity for real numbers. It's the same idea with multiplication. Multiplicative. So to find the multiplicative inverse, I'm going to need A, matrix A, times the inverse of A. The way we write the inverse of A in multiplication is we write A to the negative first power. That represents the inverse of matrix A. So that negative first power represents the inverse of matrix A. So if I have A times the inverse of A, that has to give us the identity matrix. So this is inverse of matrix A. And this is our identity matrix. Okay, so how are we going to now find the inverse of a matrix? Well, let's say I have matrix A is A, B, C, D. To find the inverse of A, what we're going to do, and it's going to be a little bit of a process, you're going to do 1 over straight lines A. This is not the absolute value of A. In the world of matrices, what does these lines represent? The determinant. So this is saying 1 over the determinant of A times. Now what we're going to do is we're going to go to matrix A and we're going to switch position 1 and position 4. What do I mean when I say switch position 1 and position 4? A is 1, D is 4. I'm going to switch them. So it becomes D here and A here. And then in position 2 and position 3, or element 2 and element 3, I'm not switching them, I'm negating them. What do I mean when I say I'm going to negate them? Make them what? Negative if they're positive, and if they're negative, make it positive. Switch their sign. That's what it means to negate it. So this would be negative B, negative C. So you switch D and A, you leave B and C where they are, but you just negate them. All right, let's practice a problem. So obviously we need to memorize this. So I'm going to say, number 1, if A is equal to 5, 4, 2, 3, find the multiplicative inverse of A. So the multiplicative inverse of A is going to be 1 over the determinant of A times D, A are switched, and B and C are negated. So the first thing I'm going to do is find the determinant of A. Who remembers how do I find the determinant of a 2 by 2 matrix? Anybody remember? How do I find the determinant of a 2 by 2 matrix? Violet? You got it. AD minus BC. We multiply on the diagonal, so we're going to have 15 minus 8. So do we all agree the determinant of A is 7? So now I'm going to have 1 over 7 times. Now I'm going to switch A and D. So this is going to be, my first element is 3, my last element is 5. And then I'm leaving B and C the same. I'm just negating them. So I'm going to have -4 and -2. And then I have a scalar times a matrix. What do we do when we have a scalar times a matrix? Ariana? Yeah, we just distribute that scalar into each element. So my inverse, multiplicative inverse of matrix A is going to be 3/7, -4/7, -2/7, and 5/7. And now I don't have the time right now to do this, but if I took A times the inverse of A, what should that equal if we multiplied them? The identity matrix, which would be 1, 1, 0, 0. Do we agree? That's the identity matrix. So if we have time later, we'll come back and multiply those to show that it does give us the identity matrix. But for now, we're going to move on. Okay, I want you guys to find the inverse by yourself. So number 2, if A is equal to 6, -7, -4, 5, find the multiplicative inverse of A. Yep. Does anybody have their answer? Violet? I got the same. Does anybody need to see me do this? So actually right now, what I want you to do is I want you to show that A times the inverse of A equals I. So I want you to show A times the inverse of A equals I by yourselves right now, and then we'll go over it. Okay, so let's do this. We're going to take the first row times the first column. We have a 2 by 2 times a 2 by 2. We're going to get a 2 by 2. So I'm going to have 6 times 5 halves is going to be 15 plus I probably should have left it as halves, shouldn't I have? No, we're good. 6 times 5 halves is 15. Negative 7 times 2 is a negative 14. And then we're going to have 6 times 7 halves is going to be 21. And then negative 7 plus 3 is a negative 21. Then we go on to the second row. Negative 4 times 5 halves is negative 4 times negative 10. And then 5 times 2 is a positive 10. Then we have negative 4 times 7 halves is 14. And then, negative 14. And then 5 times 3 is a positive 15. So then when we simplify this, we end up with 1, 0, 0, 1. Is that the identity matrix for a 2 by 2? Yes. All right, last thing we're going to do today. What have I done here now? I've added multiple operations. I have addition, I have multiplication, I have scalar multiplication, I have matrice multiplication. So we have different things going on here. Anytime there's multiple operations, what must we follow? We have to follow PEMDAS. And so according to PEMDAS, we have to multiply before we add. Do we agree? So I'm going to start off by multiplying in that scalar. So I'm going to distribute that half into all of the elements. And I'm going to rewrite everything else down. So I have 1, 2, 3, 4 plus half of 4 is 2, half of 2 is 1, half of negative 2 is negative 1, half of 6 is 3. So I distributed in the scalar. And now I'm left with addition and multiplication. What must we perform first, the addition or the multiplication? The multiplication. Am I allowed to change the order of these? No, we have to keep it as it is. So I have a 2 by 2 times a 2 by 2. Do we agree we're going to end up with a 2 by 2? So I have my first row and my first column. So I'm going to have a negative 2 plus 4. Then I'm going to have a 10 minus 2. Now we go on to our second row, and I'm going to have positive 1 plus 12. And then our last element will be a negative 5 minus 6. Okay, now we just add. What is the only rule we need to be able to add? Violet? Yeah, the matrices have to have the same dimensions. Do these have the same dimensions? Absolutely. So all you do is add the elements that are in the same position. So now I'm going to have a 1 plus 2, which is 3, a 2 plus 8 is 10, a 3 plus 13 is 16, a 4 plus a negative 11 is a negative 7. And that's our solution there. All right, we are done for today.